Hello, good day everyone. In this video, we're going to continue on the lecture for the integrated circuits biasing, which covers the constant current sources. If we're referring to the first slide, um, the integrated circuits realization of the audio amplifier. On the leftmost of the amplifier, there is a resistor together with BJT at the bottom. This circuit generates a stable DC current, which we call it I reference in the circuit. And then the other three transistors will generate the mirror of the stable DC current. So this is called the current sources circuits. So today we're going to continue on the Wilson current source. For Wilson current source, there are three transistors in the circuit: Q1, Q2, and Q3. In this case, we need Q1 and Q2 are matched transistors, which means transistor Q3 may has the different characteristic. So now we try to derive what is the DC outputs current for this Wilson's current source. Okay. So if Q1 and Q2, these are matched transistors, and VBE1 is equals to VBE2, then we should have the currents components of Q1 is equals to the currents of the transistor Q2. So that's why it's that here IB1 equals to IB2 and IC1 equals to IC2. So first of all, we derived an KCL equation as a collector of Q1. So apply KCL at this node. We have this is I reference. We have a current divider node IC1, and this is IB3. So we apply KCL. We got I reference equals to IC1 plus IB3. That is the first equation we have in the slides here. So next, we're going to get another KCL equation at the emitter of Q3. There is this node. That is the current IE3 goes to current divider node. IC2, and it's IB1 plus IB2. Since we have mesh transistors Q1 and Q2, then we have IB1 equals to IB2. So we convert IB into IC. That is IC2 over beta, and factorize IC2 in the equation. Then we have IE3 equals to IC2 multiplied by 1 plus 2 over beta. So now we want to derive the equation for IC2. Is IE3 over 1 plus 2 over beta. And we convert IE into IC. Beta plus 1 over beta multiplied by IC2 equals to IE3. then we get equation number 2. Yeah, beta 1 or beta plus 1 over beta plus 2 multiplied by IC3 equals to IC2. So that gives us the equation number 2. Alright. So what we need to do now is just combine, substitute equation 2 into equation 1. Yeah, and we can derive the expression for the outputs current, yeah, IO, and IO is equals to IC3. Okay. So we have IO equals to I reference over 1 plus 2 over beta multiplied by beta plus 2. So in fact, for large values of beta, IO, the output current, is approximately equals to the reference current in the equation. Alright. And the output resistance for the current source is next here. Is equals to beta multiplied by RO3, which is the AC output resistance for the transistor Q3 over 2. Okay. That's for Wilson's current source. So next we have a Whiffler current source. For Whiffler current source, there are only 2 transistors in the circuits, yeah, and we have matched transistors Q1 and Q2, yeah. But in this case, VBE1 is not equals to VBE2, yeah. So which means the current IC1 is not equals to IC2, yeah. So in this case, we have to refer to the DC characteristic equation for the BJT, yeah, which is IC for BJT is equals to IS saturation current multiplied with exponential to the power of VBE over VT. So we derive an equation for the transistor Q1, yeah, that is IC1 equals to IS multiplied by exponential to the power of VBE1 over VT, and this is approximately equals to the I reference, and the reference current, the DC current flowing through the resistors R1. Yeah. So from this equation, we may derive what is the voltage across the base emitter junction VBE1 as VT non I reference over IS. So this is the first expression. Yeah. So we do the same process for the transistor Q2. Yes, the output current is at the collector of Q2. So we can say that IO equals to IC2 equals to IS multiplied with exponential to the power of VBE2 over VT. Yeah. Similarly, we get the expression for VBE2 is VT ln IO, which is IC2 over IS. Yeah, that is the equation number 2. So what we need to do now is we derive an KVL expression. Yeah. We derive a KVL expression for this loop. There's a resistor I. We assume that IC is equals to IE in the BJT. So that is the current IC2 and is equals to the output current. Yeah. So we derive a KVL expression for this loop. KVL where VBE1 minus VBE2 minus IO RE equals to 0. It's equation 3. So we may substitute equation 2 and 1 and 2 into equation number 3. Yeah, that is VT ln I reference over IS minus VT ln IO over IS equals to IO multiplied by RE. Try to simplify this equation. So it's VT ln I reference over IS multiplied by IS over IO equals to IO RE. So IS in the equations cancel off. So that's why we have VT ln I reference over IO equals to IO multiplied by RE. Yeah. So that is the equation number 4 we have. So to solve this equation, we have to use the try and error methods. Yeah. The best way is we may solve this graphically. We just let the expression on the left hand side of the equation is equals to a curve, yeah, is equals to a straight line on the right hand side of the equation, and find out the intersection point that will give us the output's DC current. Yeah, we'll look at that in the next example. Yeah, and the output resistance of the current source is approximately equals to RO2 multiplied by 1 plus GM2 multiplied by the resistance seems at the emitter of the transistor Q2. Okay, so don't have to worry much about the output resistance. All right. So now we come to the example for the with the current source. Yeah. It says it's a DC supply are 30 volt and 0 volt. R1 is 29.3 K. Find the values of RE to produce IO of 10 microampere. Yeah. So this problem is quite straightforward. Yeah, because we know the output current. Yeah, we just need to find out what is the I reference, and determine the values of the resistors RE. R1 is given. So based on this expression, KVL expression, we find out what is the I reference. This is the KVL. We use this loop. We use this KVL loop to find the values of I reference. Can be AL1.